I had mentioned in class that when the trig identities popped up, I would remind you of the important ones that we're going to need to use to do some integration. So today's that day. If you remember from trig, there was a whole bunch of trig identities. In fact, when I teach it, it's always the worst exam because people just forget them or don't know how to deal with them. Luckily, we're not going to use all of them. So the main ones that we're going to use are the half angle identities for sine and cosine, which I usually call the power reduction formulas. We'll just write that down first, I guess. So we'll say power reduction. So sine squared x is equal to 1 minus cosine 2x over 2. And cosine squared x is equal to 1 plus cosine 2x over 2. Okay, so we're going to use these a good amount. And so what this is saying is that when we have sine squared of x, when we use this identity, whatever your original input is, you're going to double it. So for example here, if I had a sine squared of 3x, this is going to be 1 minus cosine of 6x over 2. Okay, so remember it as whatever your original input is, double it. So we're going to use those a lot. And then, of course, the Pythagorean identities. Now, the main one, right, this is the one that most people can remember, the sine squared x plus cosine squared x equals 1. And then there's two others, so one of which we're not really going to use because we're not going to deal with integrals for the most part of cosecant and cotangent, but we'll just go through it. If I take this Pythagorean identity and if I divide everything by cosine squared, what am I going to get? I'm going to get sine squared x over cosine squared x plus cosine squared x over cosine squared x equals 1 over cosine squared x. And what is sine x over cosine x? Well, it'd be tangent, so this one is tangent squared x, plus this cosine squared over itself is going to be 1, and then 1 over cosine is secant. Okay, so we want that one, we want this one, and like I said, there's another one that involves cosecant and cotangent, but we're not going to deal with it. But you would just go through the same process. Take the sine and cosine Pythagorean identity, and instead of dividing everything by cosine squared, just divide everything by sine squared, and you'll get the one. I always forget the other two. Honestly, I have to do this every time because I don't remember. Anyway, so yeah, we're going to use these 4 a whole bunch. So try to remember them, burn them into your retinas. Let's look at some examples then. The first type of integral that we want to look at is if we just have the integral of some nice integer power, some positive integer power of sine or cosine. So we'll deal with when we have all this other mixing of powers and sines and cosines in a little bit. But let's take a look at if we have something like this guy down here. So we have the integral of sine to the 4th x. So in general here, when the power is even, so this is the same process is going to be true regardless if it's using sine x or cosine x. All you do is you just repeatedly use that power reduction formula until you get everything in nice broken apart. You'll have a bunch of cosines floating around, and then you can just integrate that. Okay, so let's look at this guy first. So we have sine to the 4th x dx. So the first thing I'm going to do is just as a visual representation here, we're going to have sine squared x squared dx. Okay. Now let's use the power reduction formula on that purple sine squared x. So that's going to be 1 minus cosine 2x over 2, and that stuff is still squared. How do I raise fractions to powers? Well, the numerator just gets the power and the denominator just gets that power. So in the numerator, you're going to have to expand that out, use the FOIL thing. And just 2 squared is going to be 4, which we could just pull out front. So 1/4 the integral of 1 minus 2 cosine 2x plus cosine, let's write this in purple because this is one that we're going to have to do, cosine squared 2x dx. Okay. The one we can integrate, that's fine. This negative 2 cosine 2x we can integrate, that's fine. But again, now we have a cosine squared, so hence why we need to just repeatedly, however many times you need to use it, just keep using that power reduction formula until you get something that you can integrate. Now we're going to get the 1/4 times all the integral of all this stuff. So this I'm not going to change. But now the cosine squared 2x is going to be a 1 plus cosine 4x over 2 dx. And like I had mentioned a couple of minutes ago, when you use that half angle identity or power reduction formula, it says whatever your original input is, double it. Okay? So don't always just remember it as a 2x, just multiply it by 2 every time you do it. All right, now we just need to clean this up a little bit, and then we are good to go. This purple bit here, the 1 plus cosine 4x all over 2, this is really a 1/2 plus 1/2 cosine 4x. So the 1/2 and the 1 can combine to give us a 3/2 minus 2 cosine 2x plus 1/2 cosine 4x dx. Okay. Now, each of these pieces, the 2 cosine 2x and the 1/2 cosine 4x, those are, the antiderivatives are found by using u substitution. So like I mentioned in the other videos, if you need to pause the video and off to the side, actually do the u substitution, where here we would let u be 2x and here you'd let it be 4x. You'd have to do it in 2 separate integrals. It's just going to take a lot of time. Okay, so just try to get really good at doing those simple u substitutions without actually, writing out the steps. But if you need to, by all means, go for it. Oops, we're going to be done with the integral now. So the antiderivative of a constant, so 3/2 x, this negative 2 cosine 2x is going to integrate as negative sine 2x. Okay, let's just take a derivative really quick and make sure we do this right. So the derivative of sine is cosine, so that's good. And then the chain rule says take the derivative of 2x and multiply by that. So that's where that 2 comes from. So we're good. And then lastly, this guy is going to be a 1/8 sine of 4x plus our integration constant. Okay, and if you so desire, let's push that quarter through. I'm not personally going to care one way or the other if you do or not, but might as well. 4x plus c. Bam. So there's our antiderivative. So let's see if I can get it all up there for you. Okay. So like I mentioned, it doesn't matter if you have some nice even power of sine or cosine. This process is exactly the same. Okay, so just use that power reduction formula however many times you need. And yes, I promise, on a test or a quiz, I'm not going to give you something like, do the integral of sine to the 20th of x. I mean, that's going to just take forever, so it's not worth it. So yeah, that's probably the more basic of the integrals in this section. The example that we just did, we had a nice even power of sine or cosine. We did one with sine, but like I said, it doesn't matter if it's sine or cosine, the process is the same. So now let's investigate what you're going to do if that nice integer power is odd instead. So if the power is odd, what you want to do is peel off one of those factors and save it. Okay? So if we have like cosine to the 7th, you're going to pull off a cosine, save that one. Okay, so now we have a cosine to the 6th times a cosine. The remaining powers, you're going to convert to the opposite trig function. So if you have cosines, turn them into sines. If you have sines, you can turn them into cosines using the Pythagorean identity. The sine squared plus cosine squared is 1. Okay. So let's do a quick little example of that. So we'll have the integral of cosine to the 5th x dx. Okay. So I have a nice just power of cosine. It's odd. 5 is odd. So what we want to do is we want to peel off one of those cosines. for emphasis, let's put it in parentheses and use a different color just so we know we're going to save this. Okay, all of this stuff right here, we're going to save for du. Okay, so it's going to be a u substitution. Cosine to the fourth, right, I can really think of this as cosine squared x squared, and then we still have this stuff over here. Now, cosine squared is going to be 1 minus sine squared, so we'll have the integral 1 minus sine squared x squared times our purple bit. That's still there. We haven't done anything with him yet. Now, what do you suppose we need to do for the next step? Well, I have 1 minus sine squared squared, so we need to expand that green stuff out. That will be 1 minus 2 sine squared x plus sine to the fourth x times the bit that we're saving. And now we're ready to do the u substitution. We're going to let u be sine of x, because those are the ones that are inside of the powers. So put it over here, guys. So u is sine of x, du is cosine of x dx, so dx is du over cosine of x. So let's plug in all of those pieces and see what we get. 1 minus 2 u squared plus u to the fourth, and then our cosine x times dx, which is a du over cosine of x. And this is why it was important to save that factor of a cosine, so that when we do our u substitution, it cancels. Okay. So we're left with this integral now. 1 minus 2u squared plus u to the fourth du. And just use the integration power rule on that. So the antiderivative of a constant is just going to be u minus 2/3 u cubed plus 1/5 u to the fifth plus c. And like always, our last step is just make sure to back substitute what u was. So u was sine of x, so we're going to have sine of x minus 2/3 sine cubed x plus 1/5 sine to the fifth x plus c. And there is our antiderivative. Okay, so we started with the antiderivative, find the antiderivative of cosine to the fifth, and you get this giant polynomial in sines, which is probably not something that you would expect to get, but that's what it is. So again, the takeaway is, it doesn't matter if you have sine or cosine. If you just have the integral of sine or cosine to an odd power, peel off a factor, okay, save that for du, that's the first purple bit that we did, and then that remaining even power, just convert with the Pythagorean identity. So either 1 minus sine squared x or 1 minus cosine squared x. Okay, expand everything out, and then it's a u substitution with sine or cosine, whatever you started with right here. All right, so next up, I do believe, we're going to look at, how to deal with if we have an integral and we have powers of sine and cosine. It's kind of the same idea as what we just did here, but you'll see. All right, so like I just mentioned, what we're going to look at now is, instead of just having the integral of sine or just the integral of cosine, what if we have a product of them? Okay, so what if we have an integral that looks like this, sine to some power and cosine to some power? So these are handled in two different cases, but they're completely analogous. So if m, so the power on sine here, is an odd positive integer, and n, the power on cosine, is any real number, okay, including 0. If n is 0, then we're just right back into one of the cases that we just talked about. You want to save one of the factors of sine of x, and then convert all the rest of the sines to cosines using the Pythagorean. Okay? And similarly, if those roles are reversed, you're going to do the exact same process. Okay? So we're just going to look at one of those types here. So if I take, say, the integral of sine cubed x times cosine squared x dx. Whichever one of your powers of sine or cosine is odd, you want to save that one. So I'm going to peel off a sine here. And we go with that purple color again. So this will be a sine x dx. And this is, again, we're going to save this. So save for our du. Okay, so it says if m is an odd positive integer and n is any real number, save a factor and convert the remaining sines to cosines using the Pythagorean identity. So we'll have the integral of 1 minus cosine squared x times cosine squared x times the bit that we're saving. Distribute this cosine squared in. So we'll have cosine squared x minus cosine to the fourth x, again, times the bit that we're saving. And now we're good to go. All right, this is just going to be a u substitution with cosine. So I'll put this over here, guys. So u is going to be cosine of x. Du is negative sine of x dx. So dx is du divided by negative sine of x. Okay, so we're going to be doing a lot of stuff now where you're integrating trig functions and differentiating them kind of at the same step. And just always remember what direction you're going when you're dealing with derivatives and antiderivatives of sine and cosine, right? Because those negatives will flip places. So just be careful. So we'll have the integral of u squared minus u to the fourth times sine x times our dx, which is du over negative sine of x, and the sine of x's will cancel, drop out. Okay, so we're just left with this -1, which all I'm going to do is I'm going to distribute that -1 into here. It's just going to flip those guys around, just so I don't have to deal with a negative out front. So this will be the integral of u to the fourth minus u squared du. And then just power rule that. So this will be 1/5 u to the fifth minus 1/3 u cubed plus c. And as before, and as always, right, don't forget to back substitute what u is. So u is cosine of x. And don't forget our plus c. Otherwise, the guy's going to flip the table over and be very angry. There we go. Voila. Okay, so again, in recap, if you have a sine or a cosine and that has an odd power, so whichever one has an odd power, you're going to save one, so now you have an even power, and then convert that remaining even power to the appropriate sine or cosine. Okay, this process would be identical if instead of sine cubed, we had sine to the fifth. So I'd still peel a sine off. So now this is sine to the fourth. And you're going to write one of those sine squareds as a 1 minus cosine squared. But we have a squared here. Okay, so before distributing this cosine squared x, you'd have to expand out the 1 minus cosine squared x squared. Okay, then distribute. So the process is identical. It just gets a little bit longer the bigger that odd power is. Okay, but and again, it doesn't matter if it's sine or cosine or whatever we have. It'll still be the whichever guy has the odd power is the guy that you peel off and save and then convert. So just keep on going. So this video is probably going to be just a little bit longer just because there is a decent amount of cases to look at. But so hopefully you guys won't find it all too boring. Let's turn our attention to if we have powers of tangent and secant. So in general, we're going to do basically the same procedure as what we just did for powers of products of sine and cosine. So if we have an even positive power, okay, on n, which is secant, you want to save two of those. So we want to peel off a secant squared, put it to the side, and we want to rewrite the remaining powers of secant in terms of tangent, and then we're going to u sub for tangent, because the derivative of tangent is secant squared. Okay? So, first example. we have the integral here of tangent to the fifth of 2x times secant to the fourth of 2x. So the power on secant is even. So I want to save two of those guys. So I'm going to peel off a secant squared 2x, and I'm just going to put it to the side and leave it alone for a minute. Okay? And then we want to rewrite the remaining powers of secant in terms of tangents, as we're going to use the other Pythagorean identity that secant squared 2x is equal to 1 plus tangent squared 2x. So we're going to have the integral tangent to the fifth of 2x times 1 plus tangent squared 2x times the piece that we're saving. So secant squared 2x dx. And then like in the previous example, I'm going to distribute the tangent to the fifth 2x into this before we do the u sub. I mean, or you could do the u sub now and then distribute you're still going to have to distribute at some point. So we'll get tangent to the fifth 2x plus tangent to the seventh of 2x times our secant squared 2x dx. And now we're good to go for the u substitution. So we're going to let u be tangent of 2x, then du, now remember there's going to be a chain rule that happens here, is 2 secant squared 2x dx. So dx is du over 2 secant squared 2x. And then just plug in all of our pieces. So now we'll have the integral of tangent to the fifth of 2x, so that's going to be a u to the fifth plus u to the seventh times our secant squared 2x dx, but dx is du divided by 2 secant squared 2x. So the secant squared 2x's will cancel, and the 1/2 we can just pull out front of the integral. So we're left with the integral, 1/2 the integral, u to the fifth plus u to the seventh du. And then as the last 3 or 4 examples, I'm losing track of how many we've done now, just do a power rule on the u's and then back sub. So we'll have 1/2 times power rule here, so 1/6 u to the sixth plus 1/8 u to the eighth plus c, and then back substitute and then distribute the 1/2 if you desire, which I guess I will desire to do so. So we were back substituting u is tangent of 2x. So tangent to the sixth of 2x plus 1 over 16 tangent to the eighth of 2x plus c. Okay, and there's our antiderivative. So again, as a recap, if you have an integral and it has powers of tangent and secant, and the power on secant is even, you want to save a secant squared for the u substitution, convert the remaining powers of secant into tangents, and then do the u sub, and you're done. Another case to look at is, what if we have an odd power on tangent? How are we going to deal with that? So if m is an odd positive integer, so down here in this example, m is 3, you want to save a factor of secant x times tangent x. So you want to peel off 2 things, a secant times a tangent. Okay? Because we're going to make a u substitution for what? Secant. Now, it's going to be the same idea. Save, you'll have some even power of tangent left. Use the correct Pythagorean identity to rewrite everything in terms of secants. Do the u substitution, and then you're good. So we have here the integral of tangent cubed x times secant to the 2/3 x power. Okay, so this isn't going to matter. The only thing that we care about is right here. Okay, we have a odd power on tangent. So we want to peel off a secant times a tangent. So if I take a tangent out of tangent cubed, you're left with tangent squared x. And if I take a secant out of secant to the 2/3 power, you are left with a secant to the negative 1/3 power. And we're saving this secant x tangent x. So again, we're going to save this for du. So don't lose track of it when you're doing all the simplification here. So save for du. Okay. Now it says if m is an odd positive integer, which we had 3, save a factor of secant x tangent x, ding, and convert the remaining powers of tangent, so we have this tangent squared, into secant. So we need to rewrite tangent squared x. So tangent squared in terms of secant is secant squared x minus 1 times our secant to the negative 1/3 x times the stuff that we're saving. As before, distribute the secant to the negative 1/3 into there. So I have secant squared times secant to the negative 1/3. So you're going to add the powers together. So 2 is a 6/3. So you have a 6/3 minus a 1/3 gives me a 5/3. So secant to the 5/3 x minus, well, 1 times that thing is just that thing. So times the stuff, again, that we're saving. And now we're good to go. If we let u be secant, the derivative of secant is secant tangent, and those guys will cancel. So u is going to be secant x. Du is secant x tangent x times dx. So dx is du divided by that stuff. So divided by secant x tangent x. Plug in our pieces. So u to the 5/3 minus u to the negative 1/3 times the bit that we saved. So secant x tangent x times dx, but dx is really a du over secant x times tangent x. And those go away, which is good. Just rewrite what we have left. So we're doing the integral of u to the 5/3 minus u to the negative 1/3 du. So again, just go ahead and do the power rule on this. So we're going to get really good at adding 1 to fractions, like I said in class. So 5/3 plus 1 is 5/3 plus 3/3, so 8/3. So we're going to have a 3/8 u to the 8/3. Add 1 to a negative 1/3 gives you a positive 2/3. So minus 3/2 u to the 2/3 plus c. And then always remember, back substitute what u is. So we're going to plug in secant x for u. So 3/8 secant to the 8/3 x minus 3/2 secant to the 2/3 x plus c. Okay, bam, there you go. So that's the process for if you have an odd power of tangent. Okay, so there's another case, and we'll do one of them in class. It's on the worksheet. But if m is even and n is odd, so if we have like tangent to the 4th and a secant cubed, or even if the tangent to the 0, so that's gone, so just something like secant cubed, which we'll look at in class, what you usually need to do, so usually use integration by parts. It's kind of the only way to do it. But like I said, I'm not going to go into that for the video. We'll do one of the ones on the worksheet is this integration by parts process. So I'll have you guys work through a lot of the problems, and then we'll probably just have to work through that one as a group. But we'll see how it goes in class. So we're gonna have one more type to look at, and it's just the what do I do if I don't see what's going to happen. I think it's a good way to look at it. So we've worked at like 4, 5, 10, 30 examples. I don't know, a lot. Like I said, this video is going to be a little bit longer than the other one, just because there is a lot of cases to look at. So the last case I think is just a good one just to keep in your back pocket, which is if you can't remember or can't see the trick that's going on with the tangents and secants, maybe usually just turning everything into sines and cosines will work out for the best. So this guy here, we have the integral of tangent squared 2x over secant cubed 2x. And let's just say I don't remember or I can't think of what to do. Let's just start rewriting stuff. So this is the integral of tangent squared 2x times 1 over secant cubed 2x dx. Okay. What is tangent? Well, tangent is the ratio of sine over cosine. So the tangent squared 2x, this will be a sine squared 2x divided by cosine squared 2x times, and again, secant is 1 over cosine, so 1 over secant is cosine. So times a cosine cubed 2x dx. And we have a power of 3 of these guys, right? We'll kill off all of those guys, leaving us with just 1 here. So this will give us the integral of sine squared 2x cosine of 2x dx. Now, can you think about what you need to do? So before we go on, pause it and see if you can think about what needs to happen here, if anything, or are we good to go? So pause it, see if you can figure it out, and then unpause it and see if you're right. So what we want here is if we let u be sine of 2x, we're good because the derivative of sine is cosine and I have the right thing right there. So u is going to be sine of 2x. So don't forget about the chain rule here. We'll get a 2 cosine 2x dx. So dx is du over 2 cosine 2x. So we'll have the integral now of u squared times our cosine 2x times dx, but dx is du over 2 cosine 2x. So the cosine 2x's will drop out. And like always, we have a power of 1, or a factor of 1/2, so go ahead and pull that guy out. And just simple integral, so just power rule that. So we'll get 1/6 u cubed, right? So we'll get a 1/3, so the 1/3 hits the 1/2 is a 6th, plus c. And just back substitute our sine of 2x. So 1/6 sine cubed of 2x plus c. Okay, so like I said, the Hail Mary pass. So you just have no idea what to do. Just turn everything to sines and cosines, simplify what you can, and see if that gets you in the right direction. But anyway, like I mentioned, this video is going to be a little longer, but that's it for this. We'll just do one more for next Wednesday, which will be over partial fractions, which really is just going to be an algebra lesson. It's not going to be overly difficult integration. It's the algebra that's going to be super tedious, but you'll see.